Bonjour à tous, on est aujourd'hui sur une vidéo très spéciale. Vous êtes-vous jamais demandé comment fonctionnait ou comment crée-t-on un processeur ou même un SoC? Eh bien, j'ai cette question à poser à Stephen Robinson. Stephen Robinson, c'est tout simplement l'architecte en chef de la partie processeur chez Intel. Donc, qui d'autre que lui pour répondre à cette question, répondre précisément et enfin vous donner à comprendre comment fonctionne ce produit majeur au sein de nos produits, n'est-ce pas? Alors, cette interview sera faite en anglais et sous-titrée en français. Ne vous inquiétez pas, tout ira bien. C'est pour conserver, bien évidemment, la voix de Stephen Robinson. So, Stephen Robinson, thank you so much for agreeing to speak with me on the subject. So, the idea is to actually understand a bit more about how do you create a CPU and more so an SoC? I think no one knows that better than you.
Maybe some people, but I try.
I mean, come on, you're the CPU lead architect for Intel, right?
Yeah.
You've been there for 5 years, if I'm not mistaken?
Well, I've been at Intel for over 20 years.
Over 20 years, okay.
And I've been over all the CPUs just for maybe a year or 6 months or something like that. So it's a bit new. My background was sort of the E-core. I was there from the inception through the execution over the years.
Okay, perfect. So kind of a nice first question, right? Is like, could you briefly explain in your own words, what is your role at Intel?
Sure. So I manage the architecture team. Yeah. The architecture team, you can think of it as architecture and design. So architecture is where we try to define our targets, our goals, and the methods by which we're going to achieve them. So microarchitecture, changing parts of the design, branch prediction, execution, area, power, these all go into parts of that target. And we have a schedule, and we have a design team, and we have to right size what we want to do with what the team is capable of doing in that period of time. Yeah. So, we've got a set of architects that are amazing, and they work hard in different areas: memory subsystems, cache fabrics, etc. Okay. And then we try to deliver all those to a product on time.
Okay, yeah. I think the timeline aspect is actually something that's quite baffling to people. So we'll talk about that just a bit later. But first and foremost, what sort of education led you to this? And did you always have this in mind, like to create like CPUs and stuff, or is it a byproduct of what really interested you in the first place?
It's actually a little bit odd.
Perfect.
I grew up and my family was in desktop publishing, magazines and such, and printing presses and stuff. And so I worked there after school, in the summers, affair, right? Of course. And so I thought, maybe I'll go off to a design school or something. And I had enjoyed computers and was, math and science. I enjoyed those things. And my mother said to me, "Why would you do that? I figured you would build or design computers instead of use them." And I thought, oh yeah, that sounds more fun.
A great idea.
Right, exactly. Yeah. So I, applied to university. I loaded up my 1967 Ford Mustang and drove to Austin, Texas, and went to UT Austin. Okay. Where I got a 4-year degree, so that's the limit of my education. So I'm undereducated.
What was the theme of the?
It was
4 years?
Electrical engineering, and at the time they had a computer engineering option where you would take a couple of different classes, but it was the bulk of it was the same. Okay, and we're in the I don't know, maybe 70s, 80s. This would have been 1992 when I started.
Sorry. Actually, my date of birth, so perfect.
Okay, nice.
Yeah. Sorry about getting you a little bit older. It's just my timeline is crossed with the fact that I'm just stuck at 20 right away. So
the hair's getting a little lighter. It's okay.
Yeah, I mean, I'm not one to actually judge. So concerning processors now, right? I want to talk about the Intel way, of course, but just a bit after. First, so people can understand the work you do. Let's say we're trying to build a CPU from scratch. I know it's a bit of a tall order, but what would be on your mind to create such a product? And the first steps in building it, essentially, what are the main ingredients and how do you come up with a recipe, right?
Yep. So the very first question is the ISA, the instruction set architecture. So am I going to do something that's x86, which Intel does clearly? Am I going to try to do something that uses an ARM like ISA or a RISC like ISA or RISC-V? So the very first question is the ISA.
Okay.
Once you figured out the ISA, next you sort of have to decide what performance you're going to go after. You know, there's so many different CPUs in the ecosystem. There are
for so many different products, right?
That's right. Do I want to make a chip for a phone? Do I want to make a chip? You know, they've got these ESP32 things that people buy for home automation, right? You sell millions of those, and they can be fun little projects. So, or on the extreme end, do I want to do a Panther Lake type design? What you do and how you approach it is going to be very, very different depending on what you're targeting. So if I want to be an embedded controller, I'm going to be a shorter pipeline. I'm going to have fewer execution units. I'm going to shoot for a lower frequency most likely because the power constraints and the cost constraints are paramount there. If I'm going to shoot for lead high performance microarchitecture, then I'm going to spend a bit more on all of the decisions that we make.
Yeah, for sure. I'm curious about one thing though. What is to your point of view, and only yours, right, the most fun? Is it actually to try and break through something like a high frequency and that kind of stuff, or is it more about like trying to actually target like a very precise product?
The thing I personally enjoy more than anything in the world is the design and debug cycle. So you write a little piece of logic, or you write a little script, or you do something, and then you run it, and you test it, and then you debug it, and you fix it. And that design iteration loop is so much fun. That's where you're building something, you're creating something, you're implementing something, and watching it come alive is very rewarding.
That's kind of an instantaneous feedback loop, right?
That's right. And so that's the part I love the most. Now, in my official job title and role, deciding what IPC features that we build, exactly how we're going to break bottlenecks and improve performance, that's the other side of it that I really enjoy. And when you do that, you do it in the constraints of all of the other things, right? I can have an amazing genius feature that someone brings or somebody invents, but if we can't build it on the cycle time or on the schedule, then we have to change it and optimize it or abandon it for something else. So,
maybe keep it for later, at some point when it evolves, right? Well, now with Intel, because you're coming through a long-spanning legacy of building like processors and SoCs. So what changes in the process of building when you have such history behind you? So there's a couple different ways I can try to answer that. First of all, designs tend to be iterative, right? I have old gen, next gen, future gen. It's important to make sure you go around and you don't leave things stale for a long time. So we want to look and think about everything we've done as we move to the next generation. We don't necessarily review everything, but we want to make sure over the years we get through all the pieces so that it works together cohesively as a whole microarchitecture. I think that's definitely one important aspect. Actually, this question was motivated by the fact that we know that it's kind of an iterative process, right? So from scratch, it's easy to say like, okay, but when it comes to Intel, I'm guessing there's like a frame where you have to work a bit, like coming from certain technologies. You said, for example, that ARM isn't a thing that Intel is doing right now. So you already have some of the constraints of being at Intel. Talking about that, but what would be the best points of coming from such a huge, leader in the market?
Yeah, so we have a lot of history, and with a lot of history comes a lot of knowledge, right? So, we've been implementing x86 for quite some time.
Yeah,
right.
Quite some time.
Quite some time, yes. And so all of the good and bad parts of it, we well understand. And then, sometimes we come up with ways to completely break through and minimize any perceived expense of x86. And when we do that, now we can run faster and be more efficient, actually. So it's amazing as we grow our ISA, as we add more instructions, We like to go back and see to make sure we're optimizing that whole picture. And when we do that, we get savings, which is area and power and all the rest.
Yeah, so the knowledge is actually like the biggest thing, right?
And the people, right? Obviously, the people who have that experience is incredibly important. And then we built tools and test generators and validation environment. So if you wanted to start from scratch, you have to build all that infrastructure up as well, which, you know, can be fun, but also is a lot of work.
Yeah, it's about knowledge and support pretty much, like, you know, like the team and I'm thinking like the turnover, that kind of stuff for a little startup will be way different when it comes to Intel, right?
I think that's fair.
All right. So processors evolved to become SoCs nowadays, like essentially platforms that contain multiple chips designed to address different areas of specialized computing, such as graphics or AI. What sort of challenges come from building such an all-encompassing platform at the deep level that you're at?
The first question is, what do you include?
Yeah.
Right? How much graphics, you know, and we're building NPUs now for AI workloads, you know, USB ports, PCIe ports, you know. If I'm in a desktop, I have, you know, a million USB ports, it feels like, on the back and the front and everywhere. If I'm going into a phone or I'm going into a laptop, well, it's a little different. Yeah. So deciding what to put in is the most important thing first, right? Because if you did not put that AI accelerator in there, and everyone else did, and the world moves to doing inference and agentic AI and all those other fun things, and you didn't, it may take you a year or two to correct that and get that thing into the marketplace.
Yeah, and then you have a slow start because everyone's already started.
Exactly. Now, in terms of integrating things, you know, old PCs, desktops, the way we built it in the past was a discrete CPU, you know, maybe a north bridge that had a memory controller, and maybe a south bridge to go and do all that connectivity. And it feels like every 3 or 4 years we change that mix, right? And so we're trying to get all of it onto one chip, but now that becomes difficult because you have different voltage needs, you have different interfaces, and that adds a vector of challenge. So now we break things up so that we get the CPU on the most advanced process technology we can. Maybe we get the GPU on that advanced process technology as well, because those are our marquee, high power, high performance IPs, and you get the advantage. But then we take other pieces and we do it on a previous node for cost reasons. And so integrating all that together, that's where this whole advanced packaging thing that we've got, and all of these different ways to assemble things. And that adds a complexity. You have to, you know, sometimes you have to make squares fit together perfectly, right? Other times you can stack them. And so it feels like a whole new world in terms of how you do this construction.
Yeah, to me it feels like a motherboard on a motherboard at some point, where every step of the way you have such tiny things dedicated to everything, right?
I completely agree, right? So, you know, a 20-year-old desktop looks like, you know, a board with a bunch of chips, and now our SoC looks like a board with a bunch of chips. It's exactly right. And we're just arguing which parts go integrate with which pieces.
Yeah. Well, we started talking about like process nodes, so I've got a question about that, because, you know, process nodes have become somewhat known in the mainstream as something to look out for when commenting on new products, even though like it's some of the geekiest thing, I think, for our universe. So could you tell us about the importance of process nodes when building an SoC? What is gained from evolving process nodes, but also what's perhaps the biggest misconception regarding them?
Okay. Advanced process nodes get more expensive every year.
Yeah.
Right. So that's certainly a challenge to continue scaling and for affordability and cost.
Yeah, that's what I keep saying on my YouTube channel, actually.
Right.
Thank you for validating.
Of course, absolutely. So, you know, the smaller thing you want to print, the harder it is to do it, right? We're talking about doing things in vacuums so that we don't have molecules flying around. We're talking about particles that, you know, just the clean rooms are absurd in terms of what they're capable of. And you know, recently this EUV transition, this is major. The industry sort of resisted it for many, many years because they understood how complicated and expensive it would be. But we've embraced it now, which is excellent. So that piece of equipment is very complicated and expensive, but it actually makes the printing process a little easier in certain respects. So one of the things we did before is we used 193 nanometer light, and to print, we were printing something much smaller than that. And so we have what we call double patterning and quad patterning. And every time you do that, it's an additional step.
Yeah.
Each step means it takes longer to go through the factory. That means it takes longer for us to get our prototypes and debug them. And so that whole
to
loop,
iterate, right?
that iteration loop, that design, debug, and fix loop just gets a lot longer. So now with things like EUV, it's better, right? But again, that machine that I think we flew over on 3 different 747 cargo planes to assemble, I think you'll get to see that in the fab tour.
Quick. Maybe like tomorrow, I think, or the day after that. I can't wait, actually.
So those things are fascinating, complicated, exciting, and expensive.
Yeah.
So a new process node almost always allows you to make things smaller, and smaller helps power. The closer you get things together, the less time you spend, going from place to place, and the less energy you spend going from place to place.
Signal and electricity is that's a shorter way to actually get where they want to be.
That's right. And the smaller the transistor is, the easier it is to flip from the 1 to the 0. And so that saves energy, capacitance. So those are great things. But sometimes there are rules on what shapes and structures we can print. And so you have to be careful putting certain things next to other things. So that makes the process complicated. Ironically, the Moore's law or the computing power is where it goes together, because all of these rules get more complicated, but the computers get a little bit faster, the algorithms get a little bit better, so that we're trying to hold on to our efficiency of design through the process that we're designing itself, which is kind of interesting.
Yeah, from a TikTok standpoint, right? We kind of see that because we see evolutions in process nodes, and pretty much the hardware side of stuff for the first year, and then the second year would be the same type of gains, but more so on the software side and on the controlling side, drivers and that kind of stuff.
The platforms are complicated, and how you use it is complicated, right? If I'm on a laptop, I can be browsing, I can be playing videos, I can be running some massive Excel spreadsheet that takes all day to recalculate, right? And so you, as the user, want the hardware to behave differently depending on what you're doing.
Yeah.
And so as the use cases evolve, the software, the firmware, the reactivity of the platform has to evolve with it. And the only way you know that you get it right is with time, right? So you do things, you optimize things, and then you test them, and it all looks great. And then somebody comes in and says, "Hey, but what about this thing I'm doing?" "Oh, yeah, okay, let's tweak this and make that one good," right? So. And ironically, gaming is one of the most complicated things to get right, because anything that hiccups or stutters,
and that's it.
You don't like it, right?
Yeah, definitely not. Well, I'm actually a gaming YouTube channel, so kind of aware of that exactly. This is the hardest actually task to run when it comes to you can't have any grain of salt in the machine, whereas everything just falls apart.
I think you're going to be really happy with what you see in that domain.
Can't wait to see XC3, to be honest. But as a lead architect, it's actually quite a segue for me. What would you say are the goals that you want to achieve when conceiving an SoC? Do you have the end user in mind, or is it more about answering the needs and wants of professional partners that in turn end up serving the general user?
That's a great question, and at Intel, it's a mixed answer. So, vertically integrated companies, they're driving to a product. When Intel builds an SoC, we're not exactly driving to a product. We're driving to what we think the product should be, but we need to be mindful of the needs of the OEMs and what they think the product needs to be, right? So. Everyone's going to have a different form factor. Everyone's going to have a different cost target. Everybody's going to have a different thing that they focus, right? You may have one OEM who's fixated on games, and that's great, right? But they're going to want different things than somebody who wants a thin and light laptop that lasts for 2 days. So we have to keep all of them in mind. But obviously, we like products too. So, as we think through it, we know what we'd like to have, and we think that other people would like it. So we do a little bit of both, but we have to have that OEM flexibility so that they can meet the needs of their diverse customer.
It feels like a juggling act, right?
It is, but we touched on software and optimization, and you said software firmware. That's all part of that mix. That's why we spend so much time, effort, and energy on software, firmware, and making our machines reactive and giving OEMs the ability to control some of that reactivity so that their form factor works great.
Yeah, they can also adapt themselves some parts of the SoCs that you are actually selling.
Power and thermals is a big one, right? So someone doesn't want a fan, or somebody is willing to put a big block of copper, or somebody, there's even fancier technologies now that some people are doing. So
yeah, I was talking on the channel, but also on my reviews at different press sites, is that the SoC is one thing, the SoC, is one thing, but everything is down to the product. At one point, the same SoC will not actually behave the same. And the idea to make people understand that, it's quite difficult.
It's a real challenge, right? I can have a branded specified product, and if I put it in two different environments, you can get a different result.
They absolutely not behave the same, which is. And when we're in there, it's obvious to us, right? But for consumers that see Intel Core Ultra 9, they think that it's the same every time, but that's not how it works.
But you're assuming they printed the 9 as well and didn't just stop it until Ultra.
On
sticker,
exactly. Yeah.
Right?
Or just Intel, actually.
Yes, absolutely, yes, it's interesting.
In terms of timelines, actually, because we all have in mind that once an SoC is done, you immediately start working on the next one. Now, we know that it's actually way more parallel than that. So
pipelined is the word I might use, yes.
So could you shed a bit more light on the process of building and releasing a product and the timeline associated?
So it's really varied over the years, and some parts are getting a little longer and some parts are getting a little shorter. If I were to make it as simple as I can, once we've completed a design and we send it for manufacturing, you're somewhere between 1 year and 1.5 years until it's in the end user's hands.
Okay.
Part of that's driven by the sample cycle. Part of it's just the amount of work that has to be done. Hopefully we get it all right. Maybe we have to make a tweak somewhere. So that process takes, we used to say 7 months, and then we say a year, and then a year and a half. So anyway, it varies, and depending on the success of what you executed, that number can change. So that's once we've completed our design. Now, when we work on our design, I would say in general, we spend 1 to 2 years on writing, developing, debugging, building, optimizing power, optimizing timing, and tape out. Yeah. So from the time we sort of start the design to the time we finish it, again, it's sort of like you spend a year writing the program, writing the RTL, writing the microarchitecture, and then you spend about a year power, timing, validation, finishing it off.
Yeah. Tightening it up.
That's right. Yeah. And then what that sort of indicates is that architecture, so my team has to essentially know what we're going to build before that starts. We can overlap a little bit. So, we start a little more than a couple of years before we're ready to tape out.
Yeah.
And then market-wise, we want to bring annual value. So if it takes, 2 to 4 years, then that means we have 2 to 4 different ones at different stages of the design all the time. Okay. So the R&D aspect it feels like it's a huge bubble where sometimes something comes up, but it has to come up every year. Yep. But the bubble stays the same, really tightly integrated, right? Right. So where we try to shorten the loop is our ability to react to new information. So let's say I've got Panther Lake, and it's today, and we're going to launch it at some point, right? And I learned something new. The question is, do I get it in the one that's 4 years away, 3 years away, or 2 years away to fix it, or 1 year away? And so that's where we try to take real feedback from real systems, what's really truly going on, and going back and optimizing that where we can. So that's where, I said we take maybe a year to kind of write the program and a year to kind of finish it off. Well, but in that final year, we absolutely take in changes because we can find mistakes, we can find things we can do better, we can find new workload, whatever it is, right? And so that's an important piece to short circuit that long range planning that we do.
Well, actually, it makes me think about something because you're talking about taking feedback and perhaps adapting to, goals from the industry. So you need feedback and that kind of stuff. But I think there's a curiosity about innovation in our sector, right? Because we hear a lot of stories talking about taking bets, in this industry, like they pay off and sometimes they don't. But as a lead architect, what do you feel is your main role when it comes to innovation? Is it to inspire it, become like a muse for your product, to create it, lead the way in a sense, or to push it and essentially be the engine to innovation?
The priority is hitting your targets on time and healthy, right? Yeah. And so that is a fundamental requirement, because if I'm 6 months late, the product is 6 months late, the new
industry as a whole,
all of it is 6 months late. Well, maybe someone else in the industry steps in and gets the wins that time, right? So that's incredibly critical. And then within that is how much can we do? And innovation isn't just a new great light bulb idea. Sometimes it's coming up with an alternative that is smaller or easier.
More efficient,
exactly. And when you do that, it gives you oxygen and room to do something else somewhere else. So a lot of times we will redo something and make it smaller, and we get energy savings out of that typically, but that frees us up to spend so that we can do something else and bring more performance. The same function, smaller, gives you budget to do other things.
Yeah, that is why the idea of taking bets in this industry seems to me a bit, I'm not sure, because a lot of the industry is actually quite a cycle, and something that's really like framed and really dependent of everything, So I'm not sure, how do you feel about this idea of taking bets that is common in the media today?
So there's a place for it, absolutely. Yeah. I've got friends at startups, right? They're holding a lottery ticket. And it may not pay out like lottery tickets, but for them, I hope it does, right? And clearly they're taking a bet, right? Would we be where we are with the progress in AI over the last 5 years if people didn't take bets, if people didn't do development and innovation? So that's a necessary part of our industry. I do think it is. But I do think clean sheet designs underestimate what it really takes to pull the whole thing off. And so sometimes the bet of doing something massively different versus continuing to iterate, a lot of times those end up at similar places by the time you're done, just because maybe the bet takes longer or the bet didn't understand all of the necessary requirements. And so it's great at 7 out of 10 things.
Yeah, so it feels like the better bets are actually like mindful of the constraints of the industry, right?
I think that's right, but I acknowledge it can go both ways, right?
Of course. And this will be the last one. So of course it's a team effort, right?
Yes.
Your work with. As a lead architect, when do you feel the most sense of accomplishment? Is it when perhaps you had a breakthrough, when you finalize the design, or when essentially your own baby is integrated into your product? Like, when do you feel the most pride for your work?
When we get the samples back, we plug them in, then they work. Seriously, that's
debugged work.
That's right. Well, I mean, we get a new prototype, we put it in, and within X minutes or hours, we're running full operating systems, right? Yeah. I love that time. I get excited, right? It's getting your test result back. It's seeing how you scored on the exam, right? And so that's the part for me personally that I like the most.
No, I understand. It's the same type of feedback actually that we talked about. Yeah. So, Mr. Robinson, thank you so much for taking the time to speak with me. It's been a blast. It's been a pleasure. Je repasse en français du coup. I'll take it back to French now. Merci à tous d'avoir suivi cette vidéo. Merci particulièrement à Michael Moreau qui, chez Intel France, a mis en place cette interview. C'est pas toutes les marques qui nous permettent de parler au lead CPU architect chez Intel pour parler justement de ce genre de choses. Et bien sûr, merci à Bilal, Christophe, Kriska, Philou Nazo, Arklin, Klaus, Kai, Thomas et Ayupa pour leur soutien financier à la chaîne. C'est grâce à vous que je peux faire ce genre de sujets qui sortent un petit peu du lot. Et quant à vous tous, je vous fais des bisous.